All right, today we're going to dive into one of the most powerful ideas for building software that just doesn't die, the OTP architecture. Now, OTP originally stood for Open Telecom Platform, and it's a set of principles for creating systems that don't just survive crashes, they're literally built to expect them.
So I want you to just think about that question for a second. Most of the time we see a software crash as this huge catastrophic failure, right? But what if a system was designed with the core assumption that things are going to go wrong? What if it treated failure not as some disaster, but as just a routine, totally manageable event? Well, that is the entire idea behind OTP.
Let's just be real for a moment. Every single piece of complex software out there has bugs. It's a fact. No matter how much we test, unexpected stuff is going to happen. So the real challenge isn't trying to prevent every single failure. That's impossible. It's about controlling how the system behaves when that failure inevitably happens.
You know the drill. The common way to handle this is to wrap our code in just layers and layers of defensive checks. We've all written it. Endless try-catch blocks, if this, then that error logic, trying to guess every single thing that could go wrong. And what you end up with is code that's not just complicated and a pain to read, but it's also really brittle. And even worse, after an error, it can leave your application in some weird, inconsistent state.
Okay, so this is where OTP just flips the whole script. It introduces a philosophy that at first sounds completely insane: let it crash. But listen, this isn't about being careless or reckless. It's a totally different and way more powerful strategy for building systems you can actually rely on.
And this really gets to the heart of the mindset shift. Instead of writing tons of complicated code to prevent crashes, you write really simple code that does one job well. And if that job hits an error it can't handle, it just fails fast. The key is that the failure is completely contained inside a tiny, isolated process. And a dedicated manager, what we call a supervisor, immediately steps in to restart it in a perfectly fresh, clean state. The focus completely shifts from preventing every error to guaranteeing a super fast, predictable recovery.
So, how does OTP actually pull this off? Well, it's all built on a few core concepts that work together in this really elegant, hierarchical way. We have workers, supervisors, and the supervision tree that organizes the whole thing.
First up, everything in an OTP system runs inside what are called Erlang processes. Now, these are not like the heavy processes on your operating system. They are incredibly lightweight. You can literally have millions of them running at once. But here's the real game changer. They are totally isolated. They share zero memory. In most multi-threaded systems, shared memory is a constant source of bugs and data corruption. Here, processes can only talk by sending messages. So what does that mean? It means if one process crashes, it is physically impossible for it to corrupt the memory of another one. The failure is perfectly contained.
So what's a worker? Well, it's pretty much what it sounds like. It's a process that has a job to do. Maybe it's handling a web request, or processing a chunk of data, or managing a network connection. It's designed to just focus on its one specific task and nothing else.
Now this is the magic ingredient. A supervisor is a special kind of process, and it doesn't do any of the real work itself. Its only job is to watch over a group of other processes, its children. And if one of its children dies, for any reason at all, the supervisor's job is to kick in, follow a set of rules, and bring it right back to life.
So how does the supervisor even know something went wrong?
It uses this really neat built-in mechanism called linking. When a supervisor starts a worker, it creates a link between them. You can think of it like an invisible string. If the worker process dies, that string breaks and it automatically sends an exit signal straight back to the supervisor telling it exactly what happened. This isn't some add-on library. It's baked into the core of the system.
And these workers and supervisors aren't just in some big flat list. No, they're arranged in this powerful hierarchy, what we call a supervision tree. This means you can have supervisors that watch over other supervisors, which then watch over workers. You can create these incredible layers of fault tolerance that cover your entire application. Okay, so let's walk through the whole recovery loop. It's so simple and so fast. First, a worker hits a bug and crashes. Bam! Instantly, step 2, that broken link sends an exit signal to its supervisor. And finally, step 3, the supervisor gets the signal, checks its restart strategy, and just launches a brand new, perfectly clean version of that worker. This whole thing happens automatically in microseconds, often without the rest of the system even knowing there was a hiccup.
Okay, so we've got these incredible self-healing trees. That's awesome. But how do we package them up and manage them? Well, OTP gives us a way to bundle these trees into bigger, reusable components that we call applications.
You gotta understand,
An OTP application isn't just a folder with some code in it. It's a complete, runnable component that packages up its very own supervision tree. This makes it a self-contained, fault-tolerant unit that you can start, stop, and manage as a single thing. It's really the standard way you build and reuse reliable pieces of software in the OTP world.
All right, let's bring this all together. What's the really big idea here? What's the fundamental takeaway from this whole architecture? And this right here is the big mind shift. Instead of writing code that's terrified of failure and tries to avoid it at all costs, OTP gives you the tools to just embrace it. Crashes are no longer these scary exceptional events. They become a predictable, almost boring part of the system's lifecycle. They're handled cleanly, automatically by the supervision tree, which lets the system as a whole just keep on chugging along, reliably.
You know, OTP's answer to this very question has been used to build some of the most reliable systems on the planet. We're talking telecom switches, financial trading platforms, you name it. Really thinking with this let it crash and predictable recovery mindset can totally change how you approach building software. So the question is, what could you build with it?